Let us solve the inverse of this given matrix A using its adjoint. Now, there are also other ways in order for us to solve for a matrix of any given matrices, but this topic or example will allow us to include a lot of concepts with regards to matrices and determinants. In short, by answering this one, we are going to review as well other concepts such as the cofactors, transpose, even the determinant itself. So the inverse of a matrix using its adjoint is given in this formula. You have the inverse of A is equal to 1 over the determinant of matrix A and multiplied with the adjoint of A. So we are going to solve for the inverse later, but let's start with the determinant. Aside from it being a requirement here, this process of solving a matrix using its adjoint is a result of a theorem that part of the requirement for it to be possible is that the matrix A is invertible. So we can determine that using determinant as well. So let's try to solve for determinant first. The determinant can be solved of A is the process of multiplying all the entries in this manner until return here, and this does here to this 2. So it would be a little bit confusing here, so let me just not write it here, but this would be the value of the determinant of A, or this is the process. Let's start with 2 times negative 1 times 3. I have negative 6. All the movements from upper left to bottom right is a positive, or I mean addition. In addition, we are going to add all of them, and all the products from upper right to bottom left would be in subtraction. So we have this again, 2 times negative 1 times 3 is negative 6, to be followed with 5 times 0 times 2, that's 0. Then 5 times negative 1 is negative 5 times 4 is minus 20. All of this will be subtracted by the other flow, from upper right to lower left. 5 times negative 1 times 2 is negative 10. Again, subtraction, all of them. So I'm just trying to include them in a grouping symbol so that whatever be the result here will be subtracted to the previous. So let's continue. We have 0 times 4 times 2 is plus 0. 3 times 5 is 15 times negative 1 is minus 15. So we'll have here minus 26 minus negative 25, which will give us a determinant of negative 1. Now, aside from this, again, being a requirement of the formula, we also need to solve for this because, again, the requirement for this process is that the matrix is invertible. If ever, just if ever, this is 0, in short, we will not proceed with the rest of the processes that I'm going to present later, for it already gives us the idea that matrix A is not invertible. That would mean we will save time. So this is also, again, aside from it being a requirement of the formula, it's also good to determine here, and we are sure that A is invertible since determinant of A is not equal to 0. Next here is, since we already have the determinant, let's look at the adjoint. The adjoint of A is the transpose of a matrix of cofactors of A. I repeat, the adjoint of A is the transpose of the matrix of cofactors of A. So we're going to attack it step by step. Let's start with cofactors of A. And after all of these cofactors will be solved, we'll have its matrix and take its transpose to get our adjoint. The cofactors is of each entry in the matrix of A multiplied with a negative 1 raised to I plus j. Let's do it like this. For the cofactor of the entry in 1, 1, meaning this one here, we're going to take its minor. The minor is the submatrix of this given matrix where we are going to exclude this the same row and column of the said entry. So the cofactor of the first entry, or the entry in 1 1, would mean the result of this the result of this subfactor as its minor to be multiplied with a certain quantity later. So it will be like this. You will have negative 1, 1 plus 1, that's I and j, times the minor of your submatrix here. So it's the minor of submatrix is also considered as the determinant of this submatrix here. The determinant of that is 1 times negative 1 times 3 is negative 3 plus 4 times 0, 0. So the cofactor of the first entry, this is positive, so you will have negative 3. The cofactor of entry 1, 2, meaning this entry here, we're going to remove this into our mind, these two, its row and its column, living with these entries as part of the submatrix, and we are going to take its minor. So the minor is again the determinant of the remaining. So 1 times negative 3. But first, same thing here, negative 1, 1 plus 2. This is very important because if you are to forget this process, then there is a problem later on the resulting cofactor, and definitely on your inverse, which uses the adjoint of A. Then you have negative 3, 2 plus, sorry, this is minus, by the way. Okay, let's use minus here so that it would be true to all. Okay, and then minus 2 times 0 is 0. This is negative 3, but this is also negative, that's why you have positive 3. Next is the cofactors of 13, meaning removing this row and column. So you have 1 times negative 4, negative 1 times 4 is negative 4. But again, you have this, negative 1, 1 plus 3. And then, because you're removing this portion here, so you have 2 times negative 1 is minus negative 2. Okay, minus negative 2. This is positive, that's double negative property plus, so negative 4 plus 2 is negative 2. Continue, I'm going to write it here, the other cofactors. Cofactors of 2, 1. Negative 1, 2 plus 1, and since this is 2, 1, 5 times 3, you have 15, minus 5 times 4, because this is the, this is 2, 1. So 5 times 3 is 15, minus 5 times 4, so you have 20. But negative, and this is also negative, therefore your cofactor on entry 2, 1 is positive 5. Negative times negative. Cofactor of 2, 2, negative 1, 2 plus 2, this is positive. So you are removing this portion of a cross here. So 2 times 3, you will have 6 minus 2 times 5, 10. So you will have positive, this is negative, negative 4. The cofactor of 23, the entry 2, 3, you will be having this one. Remove this and this. I have so many scribbles here. So again, this is what will happen. 2 times 4 is actually 8, but you also have here negative 1, 2 plus 3. And then you have 5 times 2. So minus 10. You will have negative 2, but this is also negative, so you have positive 2. Let me copy here again the matrix A because I have so many scribbles already here. So matrix A is 2, 5, 5, negative 1, negative 1, 0, 2, 4, and 3. So let's continue with the cofactor of NC31, this and that. Okay, so you will have 5 times 0 is 0. So you will have here equal to, but you still have negative 1, 3 plus 1, 0. And then 5 times minus 5 times negative 1, negative 5, double negative property, you will get 5. Next, the cofactor of 3, 2. And because of this would be negative. Don't forget about that. 2, 2, 3. So 3, 2 rather. 3, 2. 3, 2. Okay, that's the process. So you will have 2 times 0 is also 0 minus 5 times negative 1. So you will have negative 5 as well. This is also 5, positive 5 here. But because of this, that's negative 5. Don't forget again the concept of this. Because this is just the minor. But this is the entire cofactor. And finally, the cofactor of 3, 3. You will expect this notation here or expression to be positive. So whatever the result here would already go. So you have here this and that. That's 3, 3. 2 times negative 1. You have negative 2. 5 times negative 1. So minus negative 5, double negative property. You will get here a result of positive 3. Now these are the cofactors. We are not yet done because our goal is for the adjoint. If we are to come up with a matrix of all these cofactors, let's say all the entries, negative 3, 2, negative 2. Next, these entries here, 5, that's 5, negative 4, and 2. And then you have 5, negative 5, and 3. These are your entries for the cofactors, or the matrix, the matrix of cofactors of A. If we are going to get its transpose, this is what you call as the adjoint of A. So the transpose of the matrix of cofactors of A. So transpose, you will still have negative 3, 4, 3 here, and then you move all the entries from column to row respectively. Negative 2, positive 5, negative 5, and positive 2. This is your adjoint now. So to finish our inverse, these are formula. Let me copy the formula here. So the inverse of A using its adjoint is the result when we have 1 over the determinant of A times this adjoint here. It's in a formula, so let me have here adjoint of A. So you have 1 over, you determined earlier here, let's make this one here, that's right, negative 1. So you will have negative 1 times your adjoint, negative 3, 5, 5, 3, 4, negative 5, negative 2, 2, and 3. So for this, your inverse using the adjoint of matrix A is the product of negative 1 times all of these same entries here. So again, the result shall be positive 3. You will have negative 5, negative 5, negative 3. You will have positive 4. For a while. Where's the 4? There was negative 4 earlier. We got negative 4, negative 4. So negative 4, negative 4. You have positive 4. You have positive 5. And you will have positive 2, negative 2, and negative 3. This is the inverse of the given matrix using its adjoint. As mentioned, this might be a little bit longer, but when solving the inverse of the given matrix using this, you came across, or you were able to review determinant, the concept of invertible or not invertible. The cofactors will also include a portion of it, which is the minors of the entries, and you will have your transpose before you have this process, which also includes the product of a scalar and its matrix. This is the inverse of the original given using its adjoint. Thank you for watching.